Buongiorno a tutti. Good afternoon, everybody. I warmly welcome Professor Jean-Marie Lehn to Istituto Lombardo, Accademia di Scienze e Lettere. I wish, first of all, to say a few words about the history of this academia and of this room in particular, we call Sala delle Adunanze, in which the institutional and cultural activity of our academia is held. The institute is located in Milano, in the Brera district. It is the site of protection and conservation of a rich and precious archival of book heritage, which is a point of reference. I have to say, with a strong imprint of interdisciplinary research, higher education, and culture in general. The Institute was founded in 1795, so more than 200 years ago, by Napoleon Bonaparte, who in the constitution of the Cisalpine Republic established the birth of the National Institute in charge for collecting discoveries and perfecting the arts and sciences, following the model of the Institut de France. In 1810, Napoleone established the headquarters of the Royal Institute of Science, Letters and Arts in Milano in the Brera Palace, in this building, in this room where we are now. The Institute at that time was a point of reference for government action, for lower and higher public education, and for the university. Furthermore, the Institute allocated parts of its funds to establishment of prizes related to the solution of problems in medicine, science, arts, and politics. So, an activity with a strong public impact. Even today, the Institute distributes around 90,000 euros a year in prizes and scholarships for researchers, students, and teachers. In 1859, the Institute came under the jurisdiction of the Italian government and acclaimed as its president Alessandro Manzoni, who was later named honorary president. As you know, this year is the 150th of Manzoni's anniversary death. Finally, in 1959, with the new name of Istituto Lombardo, Accademia di Scienze e Lettere, the institute was transferred to the prestigious Palazzo Landriani, bordering the Brera complex, where the academy has a second location. Now, let's go back to this room where we are now. In more than 100 years, hosted the most illustrious personalities, not only of the Italian history, and has witnessed the progress made by man and science over more than 2 centuries. I believe this is a worthy setting for this beautiful event, which is the lectio magistralis of the Nobel Prize for Chemistry, Professor Jean-Marie Lehn. Chemistry towards life and for life is a well-established concept within chemical scientists. However, as you know, among the unskilled people, there is still a great and widespread misunderstanding about the fact that chemistry is the origin of pollution in the most extended meaning of the word: air, water, land, living organisms in general. So one reason more to greatly appreciate the presence here at Istituto Lombardo of the 1987 Nobel Prize for Chemistry, Professor Lehn, and the topic of his lectio magistralis, Steps Toward Life Chemistry, is a realistic and fantastic message. Professor Luisa De Cola will properly introduce Professor Lehn to the audience. Before, I just want to make a few comments. Selectivity and complexity, an orderly complexity, are the characteristics of nature and of the living organism. Chemistry plays a fundamental role in governing in such sense the planned and selective transformation of molecules. Professor Jean-Marie Lehn pioneered these fundamental research concepts. Therefore, to conclude my comment, a particular thank, dear Professor Lehn, since you dedicated your scientific life to problems at the interface of chemistry with biology and physics, which is the essence of nature and life. Lehn research results have opened a large range of further applications far from being ended today. I'm sure we'll all appreciate very much the great privilege of listening at the lectio magistralis of the Nobel Prize, Professor Lehn. Grazie.
Thank you, Stefano, for this very nice introduction also about the Institute, because many people, I think, it's the first time they are here, so it's a pleasure indeed to be in this academia. And I would like to also personally thank Jean-Marie for accepting this invitation to give a talk here today. He has been very busy in these last 3 days in Milano, so I really appreciate his time to be with us, and especially last night to be with the students at the Pint of Science. So just a few biography, because of course all of you knows about the Nobel Prize, but maybe not everybody knows about a little bit of history about Jean-Marie. So Jean-Marie was born in Alsace, in a small village called Rosenheim, and he studied at what at that time was the Université Louis Pasteur, that then changed name in University of Strasbourg, but at that time was still called Université Louis Pasteur. And from the beginning, he was very interested in many different things, because many of you knows probably that his father was a very famous organist, and he started to play music in a rather early age, so he's a musician. I had the privilege to hear Jean-Marie several times playing the piano, and tomorrow, who wants to join us at 8:45, we will meet at the Duomo, the cathedral, so he will play the organ in the cathedral, that is the second largest organ in Europe. So he was interested in music, but he was interested also in philosophy, in science, in mathematics, and so for him it was probably not so easy to decide what to study, but fortunately for us, he decided to study chemistry. And he was attracted by organic chemistry, but he was also very much attracted by physical chemistry. So he was very much interested in NMR, in the properties of the molecules, so in the relationship between the chemical structures and the properties that the molecule had. And so finally, after he finished his PhD, he decided to spend 1 year with Burns Woodward at Harvard University. And there he started indeed to work on a very fascinating project that was the synthesis of vitamin B12. And he was not satisfied to do only chemistry in the lab, so indeed he joined also the group of Roald Hoffmann, a very famous computational chemist. And he was indeed one of the witnesses of I would say, the starting of the Woodward-Hoffmann rules that we studied indeed in chemistry. In 1970, he was appointed as a professor in chemistry at the Université Louis Pasteur, and 9 years later, he also joined the Collège de France as a professor in molecular interactions. Well, as already mentioned, he received his Nobel Prize in 1987 for his studies on molecular recognition. So in other words, for those who are not chemistry, the way a receptor molecule can recognize selectively and bind a substrate. And already from this definition, you understand that his interest was also towards biology and medicine, so not only on chemistry. And so his broadness in the view of science was already fantastic, in my opinion. Over the years, he developed many things, and probably everybody knows him for what he opens as a new field of chemistry, that is the supramolecular chemistry. So that is indeed the chemistry behind the covalent bond, so essentially how molecule can arrange and self-organize, so introduce this idea of self-organization, and finally introduce a very wonderful field, in my opinion, that is the dynamic combinatorial chemistry. And so, of course, if you read some of his paper, like I did for many years, you will be really inspired by his work, because the breadth of his science is really wonderful. And today, is devoting a lot of his effort towards new drugs, in particular drugs for cancer, And so you can see that he's spreading even on a different field, and he's enthusiastic as he was when I was a student in 1985. So Jean-Marie, with that, I would like to leave the stage to you. And like already mentioned, your lecture is titled Step Towards Life, Chemistry. Thank you, Jean-Marie.
So, first of all, I want to thank Professor Majorana for the invitation. It's a great honor for me to see also down there somebody I should know from our history. Huh? That must be Napoleon. Yeah, okay. He looks at me. I am very afraid, you know. Yeah, he looks very serious, and okay, we'll try to content him. So I would like to thank Professor Majorana for this very honorific invitation. I'm very happy to be here. It's a place where there is science, but there is also art, and we have something to do with art in a moment also. I would also like to thank Luisa for her introduction, for your invitation to the Institute Mario Negri, where I had a lot of very interesting discussions this morning, and we will be starting collaborations with the people there. Very interesting, especially in the field of cancer. So I was told that it's a mixed audience. I don't know how many chemists are here. We heard about chemistry and pollution already, but we'll see chemistry is not just pollution. Pollution is due to the people who misuse chemistry. I want to be clear about that. And so I would like to present chemistry in a very general way, linked to the origin of life, but not the full way, because we don't know yet. But let's see, we have to start very early. So if you allow me, I have to work, so I take off my coat. Okay. So, if we want to talk about chemistry, we have to start very early. So we are here, and the title of my talk is Steps Towards Life. It's not life, it's steps towards life. Huh? We are going along chemistry. To bring you there, we have to start very, very early on. Very early. The Big Bang. Our universe was born in a Big Bang. We can talk a bit more about that because I've read quite a lot of cosmology. It's not my field, but there are very exciting things happening there. And at the beginning, the universe was extremely hot. There was no possibility for chemistry. There were no atoms, no particles. It was very hot. And in 10 to the 43 seconds, that's very, very, very short, it cooled down. In 1 second, it went down to 10 to the 10 degrees, and so on and so on. So particles began to form, and the formation of particles led after that to the formation of atoms. And that part, this was only physics. No chemistry, no biology, no nothing else. Pure physics. But once the particles had formed, the atoms, they could make molecules, and then chemistry started around here, after 300,000 years in the evolution of our universe. And this was the age of chemistry. Then molecules became more complex by normal processes of combining atoms and molecules together. And this developed further and made aggregates of molecules. This began to define also compartments. And in some process, which we don't understand yet, but we certainly will understand, life appeared about here, on our planet. I say on our planet because life is probably everywhere. We come back to that in a moment, you will see. That's the age of biology. Luckily, it didn't stop there. The reason why we are here is that another property appeared, thinking. Otherwise, we'd not be here. Without thinking, we'd not be here. And this is Steps Towards Life. This sculpture there is very famous, Auguste Rodin's sculpture, The Thinker. And that characterizes mankind. It's much more important than life. Thinking is much more complex system also. Aha, yeah, that's a way to do it. So, the question then is, what are we doing in the universe? This is the dark slide, but don't worry, it's not a wrong slide. It's just dark. Why? Because right now, we know that the universe is composed of 68% of what is called dark energy. We don't know yet very much what it is. 27% of dark matter, which means what cosmologists know is 95% darkness. Not very encouraging. But there's 5% visible matter. 5% visible matter. And we are part of that. That's why I like to call it that this matters, that matters. This is us. Visible matter. We are part of 5% of the universe. But this 5% can understand the universe. So it's not a minor point. Now, the evolution then of visible matter, let's call it visible matter, the one which you are made of, this 5%, starts with, divided matter at the beginning, then it aggregates, condenses, makes atoms, makes molecules, then it organizes itself. Now you may wonder how, but okay, by interactions between, we'll see that later again. Then it becomes living matter, and I insist it's matter which is living, like it's matter which is thinking. Our thoughts are in the brain, and the brain is matter, it's made of molecules. And without the molecules in the brain, you don't think, you don't exist. And then maybe something even more complex can appear later on, but it's very difficult to think beyond your thinking, present thinking. But someday, you never know. You're in science, you never say it's not possible. We don't know. That's the way to say. So, that's the way towards the most complex forms of matter we know on our planet, which is just a little speck of dust in the huge universe. So what is the big question we should ask? Wait a minute. How does matter become complex? This is really the big question. That is the question which also contains our occurrence, the way we are, the reason why we are here. For giving answers, wait a minute, this thing, it doesn't really work. To the computer? No, I was told to computer. No, I have to. There's a. We need electrons. Yeah, good. Thank you very much. Okay, so to give an answer to that question, mankind on this planet has invented something which we call science. And let's look at three main domains of science. Physics deals with the laws of the universe. These are the laws on which everything else depends. The laws of cosmology, the laws of the origin of the universe, the laws in which the universe evolves. This is physics. Pardon. Then we have biology. Biology deals with the rules of life. They are not laws. The laws are given. This is the way it functions, the rules of living systems on our planet. They can be different on other planets. And then what is chemistry doing in all that? Chemistry trying to build the bridge from the general laws of the universe to how it can happen that an organism can develop on a given place in the universe and then have all these properties to live, to think, and so on. This is a fantastic mission. In fact, I would even say it's probably the most important to understand why we are here, how we evolved, and how it happened. So chemistry is not just pollution. Chemistry has a very important mission to understand how, from general laws of physics, something can happen which leads to an organism which is us on this planet, others on other planets, and who can think and who can try to understand where they come from. Now, what is the answer to this question? I can just characterize it by one word, which doesn't tell you how it happened. But it's a question of the fact that it happened by organization of matter by itself on the basis of the laws of the universe. In other words, it's not given an explanation, but it's just saying that our universe is made in such a way that it organizes from the bricks of this matter, this visible matter. And if I won't go a step further, you may disagree, but I go, that's a cosmic imperative in our universe. We cannot avoid life. We cannot avoid thinking. The universe is a built-in structure which leads to that. This can be a philosophical principle also, which we can discuss, but that's my conviction. I am not the only one. I went to thinking, but for instance, Christian Deduve, who was a famous biologist, he said that the life is also a cosmic imperative of our universe. So here we are. So now, the chemical evolution of matter has of course happened before life existed. You all know Darwinian evolution, but it started long before. Darwinian evolution concerns only living organisms, but you cannot jump from a particle to a living organism. So there must have been something occurring, some evolution, which was totally non-living matter. And so we can say that is a prebiotic, as one calls it, evolution of chemical entities, and this leads to the self-organization of non-living matter. But after that comes then, when life once existed, then comes Darwinian evolution, which is the self-organization, the evolution of organisms to more and more complexity. And this is then the self-organization of living molecular matter. Now, these big questions, philosophers in antiquity have already handled them, have asked them these questions. And we can start, just to give a reference point, but a very important one. 2,500 years ago, there were people in that small country called Greece, where sort of people called philosophers, or whatever you want to call them, like Empedocles. For him, things, and Aristotle, of course, also was the same thing as Empedocles. He made things easy. There were just 4 elements: fire, air, water, earth, and the combination gave properties. Earth and fire was dry, fire and air was hot, water and air was humid, water and earth was cold. Okay, it's a start. It's a bit primitive, but okay, it's 2,500 years ago. But at that time, there was already somebody who was thinking much better, much further than that. This was Democritos. Democritos said that matter is made of particles, and these particles cannot be made smaller. Now, this is not completely correct. But, and this was, in Greek, is that atomos, you cannot cut it. And this is atoms. So the term of atoms was introduced already by Democritos. And even, you see, in science, an idea is not sufficient. You have to prove that it is right. But it is said, although one doesn't know much about what Democritos said, what he wrote, because there is nothing left, only his disciples have written it. But it is said that he was convinced of that because you can mix things. And let me just give an example. You can go to the street in Milano and convince everybody that matter must be particles. You take a piece of sugar, you put it in water, it disappears in water, it dissolves. If matter were continuous, you could not mix this intimately. Therefore, matter is particles, and things can mix together, and we, as we sit here, are more empty space. The real particles in us is much less than the empty space which we are made of. So this was a fantastic thing, and over the years, then scientists, you can call them alchemists, philosophers, developed this idea of what is this matter made of. So it built up until, and now we make a big jump, the 19th century, when a number of people, using what had been discovered over the years, these bricks of matter, which one didn't know exactly how to put together, proposed schemes for putting them into a table, And one of the most important of them was Dmitry Mendeleev. And in 1869, he published a paper which I want to show you, because I think it's one of the most important papers ever published in science. The paper where he deals with the organization of these things which had been found, these bricks, in rows and columns. And you find here, for instance, you find, let's say, boron, carbon, nitrogen, oxygen. This is a column. Now one writes it in a row, but it's a column, and so on. In addition, he went so far, he made, that's also part of science, once you have established a scheme, you can say, if it's correct, you can make predictions. And he found empty things where he put a question mark. And these elements were discovered. They were not known at that time, they were discovered. So this is now called the periodic table of elements, and it was just organizing the properties of the elements and their atomic weight. Just seeing it as a regularity that one could organize it, and out of this, then he made this table which put together in an organized way and in a sensible way the bricks which were known at that time. Nowadays, that's the table which everybody, all students must know, and I guess everybody should know, because this is now called the periodic table of elements, the bricks of visible matter, and this organizes the elements our universe is made of. Now, when I say that, I mean the bricks which the universe is made of, and there are no others. Now, this sounds terrible for a scientist. It sounds very dogmatic. But why can one say it? Because when you count numbers, 1, 2, 3, 4, 5, 6, 7, and so on, there's nothing between 1 and 2 and 2 and 3, and here, what is happening? Hydrogen is 1 proton in the nucleus, 1 electron around. Helium is 2 and 2. Then lithium is 3, and so on. So you just count 1, 2, 3, 4, and your atomic number increases, and you come to the end of the natural elements, which is uranium, which has number 92, and this, there are some other things which you can produce in accelerators and so on. These are called the transuraniums, further than uranium, but natural elements stop at 92. Yeah, okay, I have to be careful not to get into too much things, because otherwise we'll take 3 hours. So, look at this table. That is you. And you are nothing else. At least you are the bricks. It's like when you make a house. The bricks don't make the house, but out of the bricks you make the house. So this is present in our universe. So I find this is absolutely fantastic that a two-legged organism on a little planet in an enormous universe was able to understand what the universe is made of. That's why you can hear that, do we find Mars on water on Mars? Because water is the same everywhere. And if you want to detect life on in another galaxy, you will do it because you see signs which are water and are different molecules there. So anywhere from the Earth to the end of the universe, there's no end in the universe, but far, far, far ahead, there are only these elements. It bothers me because it looks dogmatic, but that's the way it is. And the given connection between an atom A and atom B will be the same everywhere. Depending on the conditions on the planet, of course, it could be something else. On Venus, it's very hot, 400 degrees or something. So carbon-carbon bonds, they are not stable. So if there is something living, it will be maybe something else, like silicon, oxygen, and so on. So this is the playground of chemists. So chemists are like children. They like Lego. They take the bricks and they rearrange them. And they make lots of things of different nature, practically an infinite number. Now, this being said, progressively, scientists, let's call them scientists, but these people who were investigating matter, they began to sort of put things together, link atoms together to make molecules. And so from the atom to the molecule, molecular chemistry came out. And molecular chemistry, simply said, consists in taking atoms and linking them together by strong connections. Not all are very strong, but by usually strong connections, which chemists call covalent bonds. That's just one of those words which different scientific specialties introduce. And let's look at some milestones just to sort of give an idea of how it evolved. It took a long time to have a clear idea. It was again the 19th century which was crucial in understanding, and Cannizzaro, who was not much recognized, and many people don't recognize him. Cannizzaro was the first one who understood. There was a very famous meeting in Karlsruhe in 1860, and Cannizzaro, he said the right thing. He had given it in his lectures in Genoa, and many people said, there's a famous statement by, I think it was Lothar Meyer, saying, suddenly I understood, and the scales fell off my eyes. I saw. It's a very important thing. So, milestones. So 19th century, we had Mendeleev with the periodic table. We had the other progresses made. We began to understand how molecules are made. And then in the beginning of the 19th century already, Friedrich Wöhler in Germany made in the laboratory urea. Formula is given there. Simple molecule, 2 nitrogens, 1 oxygen, 1 carbon, and 4 hydrogens. Very simple molecule. But it was a great progress, a great discovery, a great achievement. Because at that time, also, one was thinking that one cannot make in the laboratory anything which is contained in a living organism without the help of a magic force, which it was called the vital force. So Wöhler, by making from what is called ammonium cyanate, which is not in organisms, urea, transformed something which was on the non-living world into something from the living world. And this destroyed the idea of a magic force, of a vital force. So that was very important also philosophically, because that means there's no magic there. It's reality, it is scientifically established. So, following that, it was mentioned in the presentation earlier, we can jump by 150 years or something like that, where I give us, this is considered as one of the highest achievements of making complicated molecules in a laboratory. Now, of course, more complicated ones have been made, but this was considered as an achievement. This molecule, vitamin B12, which you have in your body, has been built up successively from the elements, that means from carbon, oxygen, nitrogen, and so on, by 2 groups working together, collaborating across the Atlantic. One was directed by Robert Burns-Woodward at Harvard, and the other one by Albert Escher-Moser at the ETH in Zurich. And they were, of course, helped by many co-workers all over the years. There are probably something like 100 of them, and there are many steps to build it up progressively, because it's a complicated molecule. I work with Woodward, and this is my part. This is my part. I want also to point out, for those who are scientists here, and for those who will become scientists, science is a fantastic enterprise, a big enterprise. If you are part of it, you can contribute to it. Like the Duomo, if you put a stone there, that stone was yours. And in science, the same thing. What you bring is part of the whole construction. Sometimes it's a big stone, sometimes it's a small stone, but it's your stone. So this was done in the 70s of last century. And it developed further, and new molecular chemistry is not dead, far from it. New reactions were discovered, new procedures were made, were drugs, materials, new molecules, and so on. And it is developing very well and will develop for many years. But then we can ask a question, is there something else we should be interested in? Here I show you a cancer cell in blue and the killer cell, 2 killer cells in purple. What are the killer cells doing? In our body, they run around and they are supposed to detect the cells which have become transformed, which have changed. We are not normal cells anymore. And then have to destroy them when they find them, and they shouldn't make a mistake. If they make a mistake, you have a problem. If they destroy a healthy cell, not good. If they don't destroy a cancer cell, no good. So they shouldn't make an error. How do they know? If I may say no, it's not really knowing, but how does this process sort of tell the other guy who the partner is? Similarly, the HIV virus, blue particles, when it hits a white blood cell, can infect. Same thing. How does a virus get in? And we know COVID. COVID, same thing. Huh? COVID is a bunch of molecules which recognizes the place where it can infect a cell. So, the question is, how does it work? It works by contact. In other words, something happens between these large entities, which are constituted entirely of molecules. The cancer cell is a membrane, like a soap bubble. When children make a soap bubble, that's a membrane made of molecules. And here the molecules, the membrane is more common, but the cell itself expresses on the surface given molecules which can be recognized by the killer cells. So the killer cells, they know that's the partner, that's the one I have to destroy, so they destroy it. And similarly, the virus, when it hits the white blood cell, it can infect. And COVID virus, when it was finding its target, it can get in. It was a bit more complicated than just that. So molecular chemistry can be sort of said, but can say that it started with Friedrich Wöhler, and then we have proposed in 1978 to call that field supramolecular chemistry, and it deals with the, let's say, the glues between molecules, not between the bricks themselves, but what happens, a sort of a glue, not so strong, like gluing together. And the three main functions which have been studied over the years is how do molecules recognize one another, molecular recognition, how can they react with one another, and also how can they carry each other, for instance, from the outside, inside the cell, what are the processes by which this happens. Now, molecular recognition can be characterized in rather simple terms. If we stay on a simple level, but nevertheless, it's a correct one. It's not a precise one, but it's a correct one. First, you need interactions. Without interactions, you ignore. If the one molecule doesn't interact with another one, they don't do anything specific, so they ignore each other. But more importantly, as importantly, is information. You cannot recognize somebody in the street if you don't have information about that person. If how it is, what his clothes are, if he has spectacles or not. So there must be information in molecules, and indeed molecules have information. The shape and the type of building they form defines the information. This relies, so to say, in simple terms, on geometric complementarity, fitting together, and on interactional complementarity. Now, the geometric complementarity was already sensed many years ago by another great scientist, Emil Fischer. He published in 1894, and Luisa can testify for that without this is the basis of how molecules recognize one another. Of course, it's not as rigid as a lock and a key, but he said for an enzyme, biological reagent, to act on its substrate and to do something, they have to fit together like Schloss and Schlüssel. They have to fit together like a lock and a key. Note that Emil Fischer got a PhD in Strasbourg, long before, 20 years before he wrote this very famous paper. At that time, we were part of the empire across the Rhine, because we were part of Germany after the French had lost the Franco-Prussian War. And, but now we are Europeans. And I am a very strong European. That is one of the points I want to make here also. The fact that, okay, we hope that this will not start again, despite the fact that we have a war not far from you, here. Now, a perfect example of information in molecules is the following. All of you heard about the double helix of DNA. Now let's analyze what happens there. Most of you may know it. the genome of the living organisms on our planet. Here it comes specific our planet. It can be different ways of functioning on other planets. Is written with just 4 chemical letters, and rather simple ones, much simpler than vitamin B12. Adenine, guanine, thymine, cytosine, represented by these HECT, TCE letters, and okay. And this is a long, long, long strand on which these letters are connected. And the sequence makes the specificity between a tomato and an elephant. It depends on this information which is present. So this is the storage of the information. This is like a long program where a sequence of letters, and this sequence of letters determines what is the genome and the entity which results from it. Of course, a very complex process is happening after that, but this is the beginning, the storage. Now the reading, because you cannot be happy alone with storage, you have to read this information, you process it. That happens in very simple terms also. 2 of these letters, adenine and thymine or uracil, they bind together. The little dots represent something which is this weak bonds happening in supramolecular chemistry. They bind in 2 contacts, and guanine, cytosine in 3 contacts. So 2, 3, 2, 3 is a binary system. It's enough to read. Okay, one can then wonder, why did the evolution stop at 4 letters and 2 combinations? Because it's enough, probably. If you put more letters, more combinations, it probably it became chaotic. And you had a lot of errors. Even with the simple system, there are errors made, and there are processes for correcting the errors and so on, but I don't want to get into that. It would lead much too far. So, we are, if I may say, the result of 4 letters and 2 ways of recognizing them. But they can lead very far in the development of developmental biology and so on. So, chemistry has been defined and is defined currently as the science which deals with the structure of matter, how it is built up, and the transformation, how you can transform something into something else. But we must add to that it's also an information science. It's a science of informed matter, because information is stored in the molecules, the way their shape, the type of atoms which are there, the way they are structured, and a supramolecular reading and processing, which is by touching between the molecules with one another, a supramolecular processing of this information. Usually the questions I answer now, what a question I often get. Can you give an example of this difference, what it does? The example is very simple. You take a single molecule of water, HOH, angular. It's the same on only planets, as I said. A single molecule cannot boil, cannot freeze, has no viscosity, has no index of refraction. A glass of water has all that, but it's still water. So what happened? It happened that they interact, these molecules, they talk together, there's a population of molecules, and the properties of a population are much richer than the brick. And so this is a way to just tell you what is the basic difference, a single molecule of water and a glass of water, that is supramolecular chemistry. Which means we haven't invented much, it was always there, but you have just to recognize it. So then people started to make many attempts to refine the picture, making what you may call molecular receptors. In the terms of Emil Fischer, it would be a lock and different kind of keys, and some fit, others don't fit. And like the red one is fitting here, and many studies were conducted in many countries. In fact, Italy was one of the first ones. In fact, it was perhaps the first one where meetings on supramolecular chemistry were organized, long before the French, before Germans also, because they are sort of more conservative. Now, some applications in life sciences. First of all, for drug discovery, it's fundamental to understand molecular recognition, in simple terms, because a drug is a key for a molecular lock, a biological lock. You have to try, you want to have the most specific key, which just goes there, nowhere else, to avoid side effects. And then you have to design that key in such a way that it just fits the lock. Of course, when there are side effects, that means also there are some other things happening that is not completely selective, that there's no perfect drug anyway. So this is very important for drug discovery. Then over the years, we also made other things, like for instance, that kind of molecule, which is this in the blue, but the molecule is inside that blue circle, where we put a europium ion inside, and this emits light and red light, then can be used by attaching it to immunoproteins for making material diagnostics. And this machine was developed by Gérard Matisse at the company SysBio, and is now used in hospitals for immunoanalysis. Transport processes, this was recognition. I said it's also reactivity and transport. Transport processes, gene transfer. When you speak about that, and people go up in arms and say, oh, don't touch life. Of course, we should touch life. We are part of it. But so gene transfer is very important, first of all, for curing certain diseases. Like, for instance, cystic fibrosis in children who have cystic fibrosis. There's a channel, it's a chloride channel in the lungs, which doesn't function. So they accumulate mucus, and now some drugs have been found. And then they die of not able to breathe. So it's very important, and this can be, in principle, and one approach is to try to correct the gene, which is not the correct one, by simply making the correct one, and then taking it in by aspiration through the nose, and then you may hope that it will do it. It does work, but other drugs function differently. And then biotechnology, that means that you make changes in an organism, and this is called presently genetically modified organisms. So many people are afraid of it. You should welcome them, because you will be able to make the plants of the future which need much less water, which resist the heat. And for instance, that's another example which is important to see, that evolution was not around for us. Evolution just evolved. And for instance, some of the photosynthesis, you see the trees, they work very well. You see the leaves coming in spring, the flowers coming, all these nice things. But the yield, the efficiency of these reactions is very low. A lot of spent just by evaporating water, so the plant is not killed by the heat. So one has to improve on those, and now people have worked on it, and one hopes. Now, one of the most important reactions is the carboxylation. That means CO2 fixation by plants is a very inefficient process, because the plant didn't only worry about that, they had to survive in evolution. And so now some people have been able, it's coming now, it took a long time, to improve the fixation of CO2 in plants, and that will lead to, I think, very important progress. It will take time still, but it's important progress. And then also supramolecular materials, especially of biological types, and we'll show you one of those. Here it is. In 1990, we published the first paper on what is now called supramolecular polymers. That means polymers, these are plastics, which are linked by covalent bonds, but you can also make them in a supramolecular way, by sort of sticking together by these interactions. And this was in 1990. So I was quite surprised when then biocompatible materials were made out of it, when in 2013 I got an email about the fact that they had been used to make cardiovascular implants. This was a small company in Holland, in the Netherlands, where they developed supramolecular polymers for the surgical treatment of children who had a severe heart defect, because they have specific properties. And this was done, and here is the first little girl who was implanted by Leo Bokiria at the Bakulev Center for Cardiovascular Surgery, Pediatric Surgery in Moscow in October 23rd, 2013, 23 years after the initial proposal that this can be done. And over not this, we only wanted to make the basic research, just make a new type of polymer. But it was then had properties which could make it adapted for doing this kind of things. As you see, the little girl is in good shape. She's 3 months after implantation, and the surgeon is very happy too, as you can see. And we were happy too. So more than 10 children now have been implanted and so on, and they have also made now hard valves of the same materials, which allow you to have a hard valve which is not metallic and which is not from a pig, because this is usually what was done, still being done in most cases. So, what about other properties? Since the connections in supramolecular chemistry, the connections are not so strong, they're labile, one can also make materials which are self-healing. Here is a film, you almost don't see it, it's a very good film. The film is here between the fingers of my postdoc, an Indian postdoc, Nabarun Roy. And somebody is then cleaving this film in 2 pieces, and then you cut, then you superimpose the 2 pieces, you press with your finger. This is very artisanal, it's not very scientific. You just push with your thumb or with your finger. And, you wait a minute, and then you can transparent film, stretch, and it sticks. So self-healing materials, that is not the only one I give it because I know it very well, this one, but self-healing materials are now possible, and one can make them, and one can also count on the fact that they can be used for many applications. So now let's go back to the main theme, in fact, of all this process has to do with, of course, self-organization. Now, pre-organization is to make a lock for a key or a key for a lock. That is pre-organization. You design the object and you test it to see if it works or not. Beyond that is the possibility which you would like to generate to self-organize, have a system which self-organizes. Now, I don't want to go into details whether equilibrium passive or active or not, but just what is it? If you look at it, it's the spontaneous but controlled, that is very important, way of generating complicated architectures. Now, it's something where I will just give some examples, only to illustrate it, to make you sort of feel what it could be. It's a program. You have to sort of think about how you construct your molecules, which you can call the program, and then you have to read that program, and this is a design procedure. You try to, from the start, to design a process from building blocks so that at the end of it, you get a given output. And let me just first give one from biology, because biology is full of that, of course. We are self-organized. A virus is self-organized. A virus is a molecular architecture. A virus does not live. It's not living. A virus is just at the brink of life, but it cannot reproduce itself. So it reproduces itself by going into a cell, using some of the machinery of the cell to make itself and then to spread. But so how does a virus form itself? It again looks like magic, because all you need is, I give the first example of a virus which was understood, the tobacco mosaic virus. It is formed by 2,130 bricks, proteins, which have a shape and a surface such that they link together like a piece of, or like in tartar, like a piece of pie here, sort of a little bit conical, and then they bind together, and they, in an oriented way, and then they do that. They make a hole, and in the hole is the RNA. Of course, that comes from another process, but this is spontaneous. You have these particles. When they are together, you mix in the genome of the virus, and automatically it builds the final virus. This is also true for other viruses. For instance, tomato virus. There are viruses in tomato which are spherical, and where you can show that, in fact, this is also spontaneous. They spontaneously make a sphere. And it's absolutely no magic. One understands all the bases of which is organic chemistry, structural chemistry, physical chemistry, and so on. So it's a programmed chemical system, and then if you want to do something in the lab, in fact, one thing is that, like often scientists say, that if you think about it and you can do it, then you understand much more. And this has been done, indeed, by using now completely different types, nothing to do with a virus, designing given molecules which are able to interact with a given metal ion, like iron or cobalt or nickel or copper and so on. And if you design it right, then the bricks binding together in a given way by metal ions are automatically organized due to the properties of the way you make the molecule and the way in which the metal ion interacts in different ways. And then you can get many, many different types of entities which have been made in many, and I show you just the ones we have made, but there are many others. One can make a double helix and a triple helix. Has nothing to do with DNA. We just wanted to, it was a game to say, can we make double helices? Okay, yeah, one can. Can we make triple helices? Yes, one can, if one does it right. One can also make grids, where molecules can be held vertically or horizontally, and that each connection, each superposition, there is a metal ion which holds the thing together like cement. You can make this kind of circular, the colors of course are artificial, the colors are just to show the differences. But the structures are correct. This is exactly the shape of the molecules, not the colors. So these are circular architectures. There's the thing in the middle is a chloride ion, which holds things together also, but this is another part. I haven't time to do that. I will do that but when I come back to give a lecture for chemists. And this thing is a nano-cylinder. There are 3 red molecules, which are linear. There are blue ones, which are flat. And if you choose the right connector, they automatically build up this nano-cylinder. In other words, you make in the laboratory the linear molecules, you make in the laboratory the flat ones, you mix them with copper 1 in this case, that 19 components, they go together automatically. And they stop when it's done. So it's not magic, it's just using the rules of the way things assemble. Once you know them, and you can play the game. So this is also interesting for nanoscience and nanotechnology. Why? Because can we control the generation of these specific architectures? Because right now, when we build up a computer, we use components, transistors, and we put them together. Machines put them together, not we, because the machines do that much faster. And this is, of course, works very well, we know, but it's quite tedious. So the thing would be, from the component to the device, can we do it spontaneously? In other words, can we design the bricks in such a way that they will automatically go further and further? There are some examples I could give where there are 3 steps, where the first entities, they prepare the stage for the second and the stage for the third. But this is not enough, of course, because it's much more complicated. It just shows that it can be done, but the fact that you can do it doesn't mean that you achieve the final output. And this is, of course, the ultimate fabrication. Let the thing make itself. So if you want me to give an example for that, the most powerful computer we still have is the one between our 2 ears. That's the most powerful. You don't have to make it. It makes itself. In development, in a very, very complicated way, of course, which we don't understand completely, by far not. Well, someday we'll understand. But everything is there to make it, and it makes it by itself. So this is the stage of supramolecular chemistry, where you design, you put in information, you program the system, and you let it run, and you can make then functional molecular, supramolecular entities. But then, what is the next step? I will just give you a short, also in view of the time. I should try not to be carried away. So beyond that is selection. Rather than designing it to make a system where the bricks are chosen automatically by the system and which then can build up, can pick up the right bricks to make itself. And this is which we like, this requires diversity. You need different bricks so as to be able to choose among them. You need dynamics. That means you don't want the first collision to stick too strongly. If it sticks too strongly, it cannot adapt to anything. So it has to be able to separate and try something else in random collisions. This is a chemistry we have developed now since about 12 years, 15 years, where this is chemistry where the dynamics, that means the possibility of changing the system, resides in the constitution of a molecule. It's not a dynamics which has to do with motion. It's a dynamics which has to do with the constitution. It falls into pieces and it can rebuild, but in rebuilding it can do something else. I'll give an example in a moment. This leads to the possibility of adaptation. So this is what we call adaptive chemistry, where the chemical object can adapt to changes happening in the surroundings. Okay, I don't want to, it combines the two very important features of chemistry. Diversity, which is combinatorics, that's recombining things, and recognition, which is information. Recognition is information science, as I have told. So it is of interest, has been shown to be of interest for searching for biologically active substances, because another way, I give an example of that just to give you an idea without going into details. Then dynamic nanostructures and also dynamic materials. In fact, the supramolecular polymers you saw with the little girl with the implants, that is a dynamic polymer. And it's possibly very important because children, they grow. So the thing has to adjust. And after some time, then it's invaded by the normal cells and the polymer disappears. So this is the field we call adaptive chemistry. And let me just give you now an example. I want just to illustrate it, not with molecular structures, just with shapes. Suppose you have a bucket full of different bricks here, like the bricks of different colors, meaning different structures, different atoms, and they have a black dot, which is a way this reversible connection. They can connect, separate, connect, separate, but in connecting, they can connect with somebody else, with another one. So what can you do? That's a mixture. And it is, for chemists, it was a big problem to use mixtures. But what can you do with it? So, what it generates a complicated ensemble, a set of all possible combinations. This reversibility gives you access to all the possible combinations. So what do you do with it? Then you use a very simple, basic principle of thermodynamics, which most of the students must know. When you add something to it, you perturb that mixture. And you perturb in such a way that what you enter into it will bind more strongly to one than to another. And this is, for instance, if you add a receptor, it will bind more strongly to what fits best. It's again the lock and the key idea. You add a lock in a mixture of keys, but an exchanging mixture generating all the combinations, and you amplify the one which fits best. So the lock assembles its key. Now that looks ideal for drug design, drug discovery. It's not so simple, but I don't want to go into the complications. But it's basically using a principle of thermodynamics. If you perturb an equilibrium, it will reinstall itself by adjusting to what has been done. This then opens, this is good for drug discovery, has been done in many cases, and this sort of thing, the system adapts to the addition of something else. This also occurs, for instance, if you add, you are in water, if you add some acid to it, it will change and will readapt to the presence of some new entity. Let me just show you that this can be shown in a visible way, in the following way. We made two polymers, one formed of two A, B, A, B, A, B, and another one, A prime, B prime, A prime, B prime, A prime, B prime. Out of that, you make two films, and you superimpose by a corner. At that corner, you can generate the two combinations which are not present at the beginning. At the beginning, you have A connected to B, A prime connecting to B prime. What you can now generate is combine A with B prime and A prime with B. If one of these two new combinations has an optical property, you will see it. You must see it. If not, it doesn't work. And it can also be fluorescent. So I had Japanese co-workers there. They like little pictures. So they made that head of a cat where the head and the ears is polymer AB. Then the mustache, the eyes, and the inside of the ears is polymer A prime, B prime. So it's superimposed. You heat, and you get color and fluorescence where it is superimposed. So that shows that it works. Now I don't want to go into details. That means you generate the other constituents which are not present at the beginning. So chemistry started with molecular. Of course, there is also atomic chemistry, but we don't talk about that. Supramolecular then begins to be organized by principles of the way things can get together, just the principle of the structures. Dynamic becomes adaptive. The step beyond is evolutive. That's a more complicated one, where you have to use one stage to build on it, because the adaptive has a problem. If you take out what you have added, it will return to the statistical distribution. But if you then can fix the stage of adaptation, then you can build on it and make it evolutive. But that's another step. This is then the way towards complex matter. Some remarks on principles of chemistry. So chemistry has a very important property. It can create, I insist on create, you will see why also in a moment, new expressions of matter. Things which did not exist, you can make them because you have the bricks, you can recombine, like when you buy a truckload of bricks, you can build all kinds of houses with it. You have the possibility just by arranging things differently. So the book of chemistry, you have to write it, not just to read it. Of course, you read the book of chemistry which has been generated by evolution, like human beings, like trees, like flowers, and so on. But one can modify them, and this is a way to do it, and to go out of what has already been generated. Or I like also to cite music. The score of chemistry must be composed, can be composed, not only played. So chemistry has creative power, and I sort of can call it, it's the art of matter. Now, this is Leonardo, you know that fellow, he's not a minor scientist. He was an engineer, a scientist, and an artist. And he was excellent in all of these fields. He wrote something absolutely fantastic. If you read this sentence, he had seen very far ahead. You can read the top. So I don't need to read the English. But let me just point out that he used at the end of it, that first of all he said nature has produced things, but it hasn't produced everything that can be done, because we, understanding how it happens, we can use these things, the elements of the periodic table, to, and in harmony with nature, that means with the laws of physics. You cannot do something else. The laws of physics direct what you can do. And then the end of it is very strong, especially for an artist of his caliber, for one top, to create an infinity of species. So there, Leonardo, I think he could have been burned if he had written that 100 years earlier. So it's not just nature, which is very important, we are part of it, but also man-made, or woman-made, of course. So this is again Greek. This is Prometheus. Prometheus stole the fire of knowledge from the gods, and he runs away. He looks over his shoulder and says, okay, the other fellows will run behind me, will try to catch me. But they don't catch him. They gives the fire of knowledge to mankind. So he has the fire of knowledge, he holds it strong. But there is an interesting consequence. We cannot give it back. What you know, you have to live with it. You can make good use, bad use, but you cannot just erase it. That's not possible. So knowledge is not erasable. It's a progressive conquest, but which cannot be turned back unless we destroy ourselves totally. So our path leads us from looking for knowledge, more and more knowledge, and to eventually to control our control of our destiny, not letting the universe generate other things. The universe will generate many other things just by that, by natural evolution, but we have now possibility to do it by ourselves. In the past, the transmission of this knowledge was between our companion, some of our ancestors, the ape. Okay. Now, the next one, you can already see what it will be. You know, I don't know to show it then. That's the present. But then, what is in the future? Now, I don't mean by that we only shake hands with robots, but that we will transform ourselves. And we have already transformed ourselves. If you have a new crystalline, what's again? Huh? Yeah, crystalline in your eyes, that's not yours. I also have. It's fantastic. So this is not yours anymore. You are modified. You can have implants, teeth, and not your teeth. And in fact, if you get a heart transplant, you cannot say to your spouse, I give you my heart. It's not yours. So these are all pumps and beaks and things put together, and we will modify ourselves progressively. The easiest acceptable by people is when it has to do with health. But we will also do other things, and we don't know yet, and we have to live with it, and we have to know how to handle it. Now, I haven't said much about mathematics. Here is David Hilbert, one of the very great mathematicians of the past. He's buried in Göttingen. Here is his tombstone, and there are two sentences written there in this position. What are they? We müssen wissen, we must know. That is a sort of a drive. Mankind, I think, will not. It could sit there and do nothing, but it will not. I'm sure it will not. But then, what is the rest? The second one. Wir werden wissen, we will know. Now that is a vote of confidence. Huh? You say, okay, we must know and we will know. Now how much we will know, I don't know. This is for the future. Here is again Prometheus. And I encourage you, but most of you maybe are convinced already, or maybe not. Science shapes the future of humanity. Participate. Another characteristic of science, this is my last slide, which is very important. Very important. I will come up with something else. Here, Tiziano has, and like many people, have made pictures of Adam and Eve. What is Eve doing there? The fellow, the man, he says, oh, what is she doing? She will bring trouble. Huh? Trouble is coming. She picks the forbidden fruit of the tree of knowledge. This is the birth of science. Nothing is forbidden this way. You want to know, and you pick it, and you go for it. And finally, we're sitting all on this little planet, which is nothing in the enormous universe, but we have science, and that is valid everywhere. It hurts me when I say that, because it looks very dogmatic, but the laws of our universe are the same everywhere, and there is no borders. So science is, if there is a little green animal sitting there thinking with 20 feet or I don't know whatever characteristics, it will be the same basic principles. So science has no borders. It doesn't depend on whether there is a war, whether there are flags, whether there are cultures, whether there are religions, whether there are dogma. It just is like that. If we we can like it, don't like it, but you cannot escape it. Thank you.